Honestly, it's such a pleasure to be here once again. So I would like to thank Professor Diversi for the invitation. And yeah, what are we going to do today?
You can explain also why once again.
Sorry. Once upon a time, I used to be a PhD student here, and Professor Diversi was my supervisor. So this is why it is so today we will talk about the Libor Market Model and a particular extension. As you've seen from Anna's slides, one area we are working on is the solvency area. Basically, we are providing to the insurances some stochastic and deterministic economic scenarios. Yeah, we are working on such stochastic models in order to be compliant with such a regulation. So today we're going to talk about this model, which is very interesting. Probably you already heard about that, but maybe not in the displaced diffusion extension. And also we will show all the processes involved in providing some stochastic scenarios to a client. So this should be like a I won't say complete, but exhaustive, let's say, guide from the practice, from the theory, of course, the formulation, and then to the practice, inside within the solvency regulation. So first of all, we will talk a bit about the framework. I don't know how many of you are familiar with the quantities involved. I hope many of you, but we will give a introduction. Then we will see the model calibration. I will show you how to calibrate such a model. Then we will talk a bit about the discrete simulation scheme, the Monte Carlo scheme with some peculiar features. And then finally, we will validate the model and the scenarios we generate. So I think we can start. So first of all, let's talk about the quantities involved. Maybe some of you already know what is a forward interest rate. For those who are not familiar, this is the forward interest rate. Basically, it is an interest rate covering a future time range. So we have three time variables. The first one is the observation date. So the small t is when the forward rate is computed, or yeah, you can say computed. Then we have the maturity, which is S, and then we have the maturity. I think okay. We have the maturity S and the expiry T. What does it mean? Let me draw. So we have, let's see, something like that. So suppose we are here, small t equal to 0, then we have the capital T, which is our expiry, and then we have the maturity. Yes. What we know is that the forward rate could be seen as a stochastic process. And it is evolving. Let's say here you have your initial value. And then it is evolving given some stochastic model, which we will use later, up to time t. Here we fix the forward rate. The forward rate here is not evolving anymore, and then it dies. This is how forward rate is. This is the life cycle of forward rate, if you want. Why I'm saying so? I'm saying so because you have to pay attention, of course, of the small t when you are getting the state of your process, let's say. And you have to pay attention that here it is fixed, so the volatility is null. And here the forward rate value is 0. So this is, let's say, the main idea. How is it computed? It is computed from the bond prices. normally the risk-free bond prices are provided by some authorities or market data. And then here you have like the time span. So basically, normally it is computed given some day convention, but for simplicity, we will just say that it is nothing else than mathematical expiry. In the talk I will hold today, we will consider tau constant, let's say 1 year for simplicity. Okay, so first of all, let's start from the bond prices. So this part here. So this part is given from the EIOPA. The EIOPA is the European Insurance and Occupational Pension Authority. And it is deeply linked with the Solvency regulation. This is why we are using EIOPA data. So they are providing a risk-free rate, risk-free rates, a time structure, which has 150 maturities. Here, for simplicity, I stop at 60, but you know that if you want, you can show you. If you want, you can click on this link. I think. No, okay. However, it works to the right. You see. It is right. So here, if you want to play around a bit, you have the data provided by EIOPA, and you can use them for your purposes or experiments. So yeah, EIOPA is like issuing this kind of data once a month on the website. I'll show you how to do that. And here, for example, we have they use several curves. They provide you several curves. Here I use one of them, which is the spot rate with a simple volatility adjustment. Volatility adjustment is another topic, let's say, but what you have to know is that this is what you can download from the EIOPA data, and this is what we will use in the simulation. Okay, so given the bond curve, the bond prices curve, we can compute the forward curve. Because in the previous formula we have seen. So here I reported two different curves. One for September 2023 and one for 2005. Why I report two of them? Just to show you that the curves could be very different in different years, the years, let's say. So the main thing you have to notice is that in 2020, the forward curve was negative in the first terms. Okay. So let's start from the Libor Market Model, the canonical one without the extension formulation. So the idea is that we have a canonical probability space, omega f and probability measure p, and each with a filtration. Then we consider a set, a time set, called E, from which we derive a family of spanning forward rates. Here, for simplicity, once again, we said that we like to squeeze the notation, and we use FK T to denote the forward observed time T with maturity TK and expiry TK minus 1. Where TK minus 1 normally is TK minus 1. So what is interesting to see is that it exists a probability measure QK, so it is linked with such a forward rate, such that we have a driftless geometric Brownian motion. Why this thing is interesting? Because with such a very nice probability measure, the equivalent probability measure to P, we have that the state of your forward is a martingale. How many of you knows what a martingale is? Okay, now that's fine. So for those who are not familiar, it's just to say that let's say in the best, the easiest way is that the best estimation for your process is the actual value you are noticing. It's not so nice. I don't know if Professor Diversi will add something, but
Best forecast in future is
the actual value.
The actual, the current value of the
Without
the financial.
without entering much if you want. So what I'm saying is that the drift part, so the deterministic part, is equal to 0, and then you have just the diffusion part. So if you want, you can easily compute the solution of this thing. I think you know how to do it. Otherwise, just raise your hand. And yeah, something more we could say is about this diffusion part. So the sigma k is a deterministic function. Why are we using a deterministic function? Well, you can say that you have seen the stochastic volatility models and so on. You are right; they are more complex. There are less, there's less tractability if you want, but inside the solvency regulation, there's a part talking about that the models should be understandable, understood better, understood from the clients. So not insurances like say workers are not always into that deep with the stochastic analysis. So even a deterministic function, which is a Helvich deterministic function, we'll see later, could be a problem. So this is why we use a deterministic frame. Okay. So we were talking about solvency. So solvency 2, we're talking about 2016 January. It's a European regulation requiring some capital for insurance and reinsurance, setting some capital requirements to ensure protection for policyholders and beneficiaries. What does it mean? It means that they are trying to protect the market, the policyholders, and in doing so, they are asking to the insurances to evaluate their assets and liabilities to a fair value. How do we do this evaluation? This analysis. We do this analysis introducing the stochastic economic scenario generator, which is a simulator, which should be able to replicate market prices under certain assumption measure, of course. So these two will be the tests we will perform at the end of the talk in order to see if our model is good or not. Okay. So first of all, we are going to see the martingale test. What is the martingale test? Well, we are letting the bond price evolving in time by small t. Then we are discounting it by a stochastic discount factor, we introduce later. And this expected value should be the bond prices we are observing right now in the market, the one provided by Europe. And then we have the deflator test. Basically, is testing, is checking if the expected value of our stochastic discount factor is exactly what we are seeing in the market, but small t for the bond price. Okay. So here I brought the definition of the stochastic discount factor inside let's say the Libor Market Model framework about it later. Why I'm saying this? Because we represent the discount factor given the forward. We are working with the forward. The Libor Market Model is using the forwards as the quantity, like the quantity used in the simulation and stochastic process. So we are representing the discount factor in such a way that it is forward or it's forward. We have to talk a bit about beta t. Beta t is nothing else an index, which is given that that plot I showed you before. It is the first forward rate which is not expired at time t. So suppose that you are simulating and you get that small t equal to 2. Probably some forwards are expired, so you are not using them anymore in the simulation part. So this is why you should pay attention to this data. So this is the first forward rate which is not expired. Okay. So we can start then for producing the Libor Market Model dynamic, and we are introducing it under the risk neutral dynamic, even if the martingale, even if the equivalent measure we are showing before is so nice, we cannot use it inside the solvency regulation. So we have to introduce a risk neutral dynamic in order to have those tests passing. Here we have the formulation. This is the forward. This is the forward dynamic inside the risk neutral framework model. And what I would like to show you, remark, is that the diffusion part is the same as the one we have shown you before. Of course, here you need to use a different value motion, of course, because the change of measure has been done. But another interesting part is the drift part. This part, as you see, is beta dependent. So you have the pure drift is dependent on all the forward rates not expired yet. This is a very important thing to underline, because I think you have seen the Allen White factor, for example. How many of you have seen it? It is a different model. I've check maybe. I don't know how you know it. Who has never heard about it before? Okay. The important part of this is that I hope Professor Liborsi will show you, I think, mathematical finance.
Mathematical finance, but not for the students in data science.
So the interesting part is that you are like carrying the correlation between all your variables. Different let's say in the major part, the majority of models, you have just one variable. You are like interval. Here you have several variables. It depends on your structure, the horizon you would like to simulate, let's say. You also have you are also carrying the correlation. It depends on what kind of correlation you like to have. It is a parametric form. But yeah. So as I said, the law represents instantaneous correlation, which in our case is constant. For the reason I was telling you before, so it should be understandable by the client. Then I would like to introduce you the displaced diffusion extension. So as you have seen, this kind of SD leads to a normal solution for our forward. But as you probably know, if your initial value for the forward is negative, Very intuitive. So suppose that you have this, okay, and this value is negative. Here you have something else. It is a problem because in such a framework you cannot, this framework cannot lead to some positive rates. So what is the solution? Why do we need the extension? Because we shift the model. Basically, we did nothing else than adding a constant alpha. And this constant is like, you can see it as a floor for your forward rates. And this kind of floor is like, implicitly is the smallest value you can reach with your forward. So suppose that alpha is equal to 3%, 2021, so like this. So suppose alpha is equal to 3%, then what you have is that your forward rate, your state of the forward rate state cannot be less than minus 3%. So this is the Libor Market Model with Displaced Diffusion extension. Okay. So now that we have introduced the model, let's say we can see specifically what is sigma, the form of sigma, and the form of. Okay. So as I said, the sigma formulation is deterministic, but it is really say really general, because it could assume a lot of different shapes. Then I will show you in the calibration process all the admissible region in order to have a proper shape for this function. Here we have, of course, the parameters A, B, C, and D, which are constant. B, C, and D are positive constants, and A is a real. Something else you can say about the instantaneous correlation is the correlation as this one. So you have the decay, the exponential decay in and the lower level given by beta 0. So basically, the idea behind it is that all your variables involved in the simulation are positive, are correlated positively. And in the simulation part, you will see this is a huge advantage. Okay, so we can pass to the model calibration. So the main part is to define, to get the parameters A, B, C, and D, beta 0, beta 1, and alpha. This is what you need. So this is the problem in order to have beta 0, beta 1, and in order to solve this problem, what we have to do is to collect an historical series of forward rates. So you have a curve, let's say bond prices, then you have your forward rates, you compute your forward rates, you get an historical series of forward rates. And then what you have is that you have an historical correlation, which is given by a rho. And then let's say the model correlation, the one we have seen in the slide, depending on beta 0, beta 1. So minimizing the distance between these two historical correlation and the model correlation, we have our beta 0 and beta 1. And then what we need to do is to get the ABC, and D, which are our parameters for calculation. To get this, what we are doing is we observe some derivatives quote in the market, let's say swaption in this case. We have the swaption prices, and we have a more closed formula given by the model, given some approximation. What we are going to do is to minimize once again the relative distance, let's say, between the the model price and the price observed in the market for different maturities and for different tenors, for all the tenors you have, for all the maturities you have, basically. Or if you are interested in, I don't know, simulating, let's say, up to 3 or 4 years, you can use this option you are working. And here, once again, there are some constraints. So we have to pay attention that A is less than 1, B is including this range, and so on. And here, condition 5 and 6 are those I was saying before that are like ensuring that you have a really nice shape. Basically, if I'm not wrong, condition 6 is about the first derivative, the UP, where you would like to have the maximum, let's say, of your function. Okay, so here we have some let's say, calibrated parameters. And what I would like to show you once again is the differences between September 2022 and September 2023, even if it's just a year. Why I'm saying so, because from December 2024, the interest rates are raised in such a way that alpha is not mandatory anymore right now, then the future who knows. But what I would like to show you is that this model is really general, let's say, general in such a way that it can handle different market situations. So, yeah. As you see, that's maybe a Libor market, as you see, beta 0, beta 1, particularly, is really small. So it means that the correlation is really high. Beta 1 was the decaying parameter for the exponential part.
Can I ask a question?
Yeah.
Why do you have to calibrate it? And what's the calibration?
Because what do you mean with what do you mean with both the calibration?
No, what is calibration?
Calibration means that you have a model with some parameters, and you attribute some values to those parameters in order to use those parameters and the model in a simulation set.
Okay.
Okay.
How I can recognize if my choices are the right ones?
Okay. Good point. So in the model validation part, I will show you that the parameters found in the calibration procedure are good enough. The best idea, if you have some doubt like you, is to calibrate the model, so attribute the values to your parameter, use your model in a Monte Carlo simulation, and using the Monte Carlo simulation, trying to retrieve the price of the instrument you used in the calibration procedure. This is what I would like. This is what I would do. I don't know if I answer your question.
Well, yeah, more or less. But why, for example, why do you need 1 year of data?
No. Sorry, it's not 1 year of data. This is a photo on September 24, 2022, and this is another photo for the end of September 2023. The point is, I would like to show you the differences between two different calibrations, even if the time span is just 1 year, but the market conditions changed a lot.
Okay.
For beta 0 and beta 1, of course, we have an historical series, which is we are using like 1 year of weekly simulations.
So how many days did you use to calibrate?
To calibrate which part? You mean
the parameter?
Beta 0 and beta 1 part, because the calibration procedures are different. So if we're talking about this, we are using like 1 year, 1 of these two weekly observations.
Okay.
This is just 1 day.
Why this difference?
Because this is a calibration market consistent. So we have a calibration which should be market consistent. It means that if today I'm observing some market prices for the swaptions, I would like to retrieve those prices. And what I need to use is just this information. Of course, the underlying and the swaption prices. nothing else. And then if I would like to use the correlation formula showed you before and using a historical calculation, what I can do is using historical data of historical series of forward rates and compute historical correlation and minimize the distance between the parametric one. Historical.
Okay.
Then, of course, these values are used to get those. Okay.
So, which tools do you use in order to use this calibration?
Good point.
In a particular way.
Nice. All right. So what we have done also with Fabio is to implement this model from scratch in Python. Then we port it in C#. Since the Python part was a kind of prototype, then after like, so we spent let's say months if you want to get a proper model. I will show you later in the model validation part. And for example, the calibration part is like is performed also right now in the Python. So the C# part is like asking, requesting calibration on the Python module. Basically, this is what we are doing. Did I answer? Do you want to know something more about that? Okay. So there is an API, of course, so we are requesting the market model.
Maybe you would use a command or something like that in order to be.
You know, but if, okay, for example, this model, if I'm not wrong, is available in MATLAB.
Okay.
But it is not like transparent if you want, because someone else did it. So if I have to explain to the customer why this value was reached in 2050, I cannot say it because I didn't do it. I just put some values inside the machine.
You want to take your own responsibility.
From the machine. And yeah, this is what I was saying. So these are some calibration parameters. And then let's pass to the discrete simulation scheme. So of course, the solvency regulation is requiring you to project those forwards, right, the forward rates into the future. Maybe the time structure, so the bond prices in the future. How are we like projecting the forward rates into the future is for the Monte Carlo simulation. In here, I will show you some nice trick, let's say, or some like future speed. First of all, we apply a transformation to our shifted forward rates, and we apply the interval formula. Why so? Well, if you notice, this is the scheme, the discrete scheme. We are using the simulation. And what I would like to show you is that here the diffusion part is no more dependent on the state. Let me show you once again the state is divided by this. So this is a really nice part. And moreover, this kind of scheme ensures that you have this kind of scheme ensures that the distance between your approximation and the exact solution is bounded by delta t. So it is really nice to have such a result. Yes, and here I've just revised it. Of course, here we have Maybe I didn't talk about the noise increments. I suppose you know about that, but let's look at on if you want about that. Here we have the noise part. The noise part here. Sorry, this is not that, but this is this. Sorry for that. This is just it. And yeah, well, here what we are saying that is that this is nothing else that some independent Gaussian shocks. So we have that this is the noisy part, the random part, let's say the stochastic part. Here, reference if you want to know a little bit more about the numerical part of this, you can refer to the talk. And their work in 1995. Okay, then I will show you another feature we introduced in
Sorry.
model, which is the predictor corrector.
From a very practical point of view,
Mhm.
in order to implement, for example, Formula 9 or even 10, when you talk about Gaussian shocks,
Mhm.
From a practical point of view, what do I have to do?
Perfect. So what you have to do is use whatever random package you are, NumPy is okay. Suppose, and then you extract a sample from a Gaussian distribution. This Gaussian distribution. So this is this part is distributed as a Gaussian with mean 0 and variance delta t. Okay. So what you have to do is just to take a sample from this distribution. Then you have, I don't know, suppose that you would like to have 100 simulations for like, I don't know, 10 time steps, let's say. So you have a matrix of noises. Each element of this matrix has this distribution. So it is a Gaussian with mean 0 and variance delta t. And of course, you will let the model evolve according to this noise. At each t, you will have a different state for your process. You use that value inside this formula, you go. I don't know if now this the last part, the last feature we included in this model is the predictor corrector. This is nothing else that a feature done in order to reduce the variance between the time steps. So basically, we are doing nothing else than averaging the drift. So we are at time t, then we have our drift at time t plus delta t. We are averaging such a drift, and then we are using the same noise in order to let evolve the process, but with a different drift. This one. Once again, if you want to see more, you can refer to this work. It is included in the references. Nice. Let's pass to the model validation. Okay, so as I was saying, the goal is to use the bond prices and test if the bond price is simulated, because we are talking about small t, no more 0 here. 0 is we are observing right now the bond prices. T means that we let the bond prices evolve at t with one unit. So this bond price is given by this formula. Once again, you see that here we have explicitly reported in the forward. And what we have to test is what I show you at the beginning. That's from that first. Yeah. So we have to see that the discounted bond prices is equal to the bond price I'm observing right now. And the expected value of my stochastic discount factor, which is given by this not so nice formula, should be in expectation equal to the bond I'm observing at n0. Okay, so some results. Here we have the deflator test. So what we are saying is that our bond curve is the light blue one, which is here. Then we have the dot orange one, which is the expected value of our stochastic indicator. And here we have the ratio, nothing else the ratio. And this is our test. As you see, this is we can deliver such a problem to the client. We are happy about it. Probably no compliance to say anything about that. Nice, and then marking the test. Marking the test is a little bit more tricky if you want, because what we are doing is that we have this ratio. Each one of these squares reporting this ratio. So on the rows, we are moving with the capital T. Sorry, on the columns, sorry. On the columns, we are moving with the capital T in the projection. The other way around, sorry. So on the rows, we are moving to the capital with capital T. So you see here we have capital T1, the 2, the 3, the 4, the 5, and 30. So you think also about the importance of having a coherent model in simulating 30 years, which is not so easy if you want. And in here you can see that the model is coherent with this feature or assumption of no arbitrage. And this is what we are saying. Okay, here we have some, if you want, some distribution over these distributions of our stock rates for the term for the. As you can see, you have a distribution which is similar to a log norm. It's not a log norm, but you can see that it is lower bounded, as I said, given the alpha value, and then it, of course, it has support. Let's say it has support. You can see from 1.70% to 16%. So also for the insurance, it is nice to have a model which is not, let's say, Gaussian, as the Allen White was saying before. So you can possibly reach also negative values for your spot rate. But here you are bounded your negative values. You are deciding which level you will reach, and then you are just increasing. So if you have assets, it is nice. Here we have another plot for 30 years. Of course, you can see that here we the initial value, of course, and the floor. Then last plot, here we have the volatility surface for our spot rate, using the parameters I was showing you before, so for September 2023. And these are the references if you want to a little bit more about the numerical scheme and also the theory if you want. Remember. So thanks a lot. That's it.
So, are there any questions, comments?
I want to say something.
If you know the order of precision concerning the calibration, the results of the calibration.
Okay, nice. I didn't include this presentation, but if you want, I can provide some values later. I would say around 5% over the mean square error.
Okay.
Over 110 swaption prices. This is more or less But then it depends on the date, but the last one I think it's around that. Is it?
And sorry, how often do you need to recalibrate the parameters?
Yes. So it depends when the client is asking for the stochastic scenarios. So right now, Solvency requires to deliver these stochastic scenarios each quarter. And so basically we are like doing this activity, the calibration step, the simulation step, every 3 months. But we developed a tool internally, which is a SaaS service. Basically, you can go in this website, in this application, and you can calibrate each day. You can simulate. You can do whatever you want. Then you have a series of output, including those validation results I showed you before, the stochastic scenarios, if you're interested, and also the calibration report. So if you want to see which are your parameters and also the data, I didn't show you some data which are like which are downloaded from data providers. I cannot show you, but for example, the EVA part can be seen. So yeah, like for solvency purposes, every 3 months. Then for other regulations, it could be monthly. For internal purposes, it could be monthly as well. So suppose that you would like to, I don't know, manage your asset liabilities, like move your portfolio location, so on. You can do such a thing every month in order to say, okay, my capital requirements are decreasing in such a situation, are increasing, so I can move my portfolio location. So it is something internal. It's not required by regulation, but I know that it is used also for that.
Are these preparation cost intensive? I mean, how
It depends. Which part?
Well, everything.
Okay.
Measure.
It depends. It depends because the entire process, which means calibration, simulation, validation, requires for this model more or less 30 minutes.
30 minutes on?
Excuse me.
Using what?
What do you mean?
What type of machine?
It is like maybe Fabio can help me with that.
No, about laptop.
Okay. So you don't use
Sorry.
you don't use, for example, AWS or something like that.
No.
Not for this. Okay. Okay.
I was thinking about the SaaS service was that you before, so I didn't know. But yeah, you can also do this operation with your laptop, and it's about 30 minutes. But then you know that the portfolio simulated is greater than just this model. So you have also some assets, so you have to calibrate them. You have to like you have a global correlation, so you have the correlation for your model. Then you have other assets, and the correlation should be guaranteed. So that means more or less.
Other question? Just the last one. The graphs you showed, let's say, essentially based on Monte Carlo.
Well, which yeah, all of them basically, because the tests are conducted in the stochastic scenarios simulated.
And the parameters are, let's say, calibrated on historical data.
Historical, or yeah, let's say historical data.
So historical data plus Monte Carlo equal output.
Plus the adjustment fee.
Yeah. Why, for example, or maybe is it possible to substitute this procedure with a completely automated one, for example, using a machine learning approach?
So
blinded.
This will be the talk of Fabio probably. Yes, it can be done, of course.
So for the answer, you have to wait to the second seminar, unfortunately. Okay. So we can stop here. Thanks again to Andrea. Maybe we can take a small break, 5 minutes, 10 minutes, then we restart. Thanks.